let me thank the organizer for organizing this seminar and for giving me the opportunity to give this talk. So this would be, so the general theme would be group actions on algebraic varieties. And I will concentrate in this talk on the simplest case, so the group Z modulo 2, that means involutions of varieties. And I guess I'd like to illustrate the general principle that a complicated ambient variety with an action of this group tends to have a complicated fixed locus. And so in this talk, I will mostly look at the dimension of the fixed locus. So let's start with a classical result in topology due to Boardman. This is sometimes called the 5-half theorem. I think it's 1966. So consider smooth closed N manifold with an involution, so with a smooth involution. So N is the dimension of X, let D be the dimension of the fixed locus. So if Stiefel-Whitney number of X is non-zero, so those invariants are defined modulo 2, then the dimension of the fixed locus cannot be too small. So N is less than 5-half of D. So as the appearance of Stiefel-Whitney number suggests, this is really about unoriented cobordism. And in fact, Boardman's proof, roughly speaking, consists in considering the equivariant version of the unoriented cobordism ring, so for involutions, and obtain certain structural results for this ring, and then deduce a theorem from those results. In particular, it's a quite indirect proof, and I'd say it does not give a clear geometric explanation for this factor 5-halves. But still, it shows the interest of studying the equivariant cobordism ring. And so in this talk, I would like to discuss, to try to do the same thing in algebraic geometry, essentially. So this means providing definition of the equivariant cobordism ring, and then when describing its structure. And and we will obtain an analog of this theorem, but we also see that we'll obtain several variations and generalizations. Okay, so so the setting is the following. We fix a base field K, characteristic different from 2, since we'll soon be speaking about involutions. So consider variety X. So in this talk, variety would mean always smooth projective. Okay, scheme. So I will be talking about cobordism, and so I will use a very elementary approach to cobordism, which is based on certain invariants called Chern numbers. So let me recall the definition. So you look at the tangent bundle of X and consider Chern classes of this vector bundle, the product of such Chern classes, say with values in the Chern ring. And now if you arrange that the sum of the indices is exactly the dimension, assuming that X is equidimensional, you end up in maximal codimension, which means you get a zero cycled class, right? So we can take the degree of this to get an integer. And in this way, you obtain a series of integral invariants associated to any variety. And as you see, those invariants are indexed by partitions of the dimension. The basic idea is to use those invariants to distinguish varieties. So to look at varieties modulo the relation of having the same Chern numbers. So let's say that two varieties are equivalent when they have the same Chern numbers. So indexed by partitions. So which means for each partition should get the same integer for x and y. Right? And look at the set of equivalence classes. This is in fact a monoid for the disjoint union, an abelian monoid. So you can consider the associated group, abelian group. We denote it by L. So it turns out that L is a ring, a commutative ring. So the product is given by products of varieties, as you can expect. So my notation will be to variety X, I associate a class X in L, like this. So this ring has been computed. I guess in topology, this was due to Chern, but here in this setting, this is probably due to Merkoyev. So L is the Lazard ring. So in this talk, it will not be really important to say what the Lazard ring is, but the point is that it's a universal object, so purely algebraic one. In particular, it does not depend on K, on the base field K. In fact, this is a polynomial ring in variable indexed by the integers. Okay, so we can do variations on this. So
could you recall, please, what is the indeterminate correspond to in this ring, please?
The determinant?
If it is a polynomial ring, what is in variable t, for example? What is t in your setting?
So this is z of variables, I guess a1, a2, and so on. So probably I should write it like this: ai for I in n minus 0. So ai lies in degree I or minus I maybe, and this is the class of a certain variety. So depending on the degree.
Yeah. My question: what the varieties are?
So it's either the those are constructed from projective spaces and mean or hypersurfaces. So probably, I guess if we want the integral version, probably we have to take linear combination. But yes, the generator are always a linear combination, I guess, of projective spaces and mean or hypersurfaces.
Thank you. Thanks.
But of course, there are probably other choices. I guess this is the most classical choices. So here we consider the variety. Well, instead, we can consider a vector bundle, say E over X. So here X is again a variety. In particular, it's smooth and projective. And let us fix the rank R. So we had the notion of Chern numbers. And here we can do something similar with the vector bundle. So first of all, we still have Tx, but now we have E. So we can also look at Chern classes of E. take the degree of this to get an integer. And well, this is similar to Chern numbers. But the difference is that now, instead of just one partition to as an index, we have a pair of partitions. And just in the same way, we can look at vector bundle modulo the corresponding equivalence relation. So here we have the class of X in L, and now we have the class of E in some group, which I denote by MR. So here MR is just a group, it's not a ring, but if we put all those MR together, we do get a ring, and in fact, a commutative L algebra. And it's not very hard to compute it. In fact, it's polynomial over L in variable indexed by the integers. And here we can choose, for instance, Pi as O of 1 over Pi. So here there's nothing surprising, I guess. But we were interested in the equivalent version of the cobordism ring, so let's try to do again the same thing. So we start with the group Z modulo 2 and consider a G variety, which means a variety with an action of Z modulo 2, X. And so to this variety, we can associate an equivalent version of the Chern numbers, right? Well, just by using the same formula, but working equivalently. So the tangent bundle is equivalent, and we have the notion of equivalent showering. But now those are not quite numbers. Those are elements in the showering of the base. Right? This is sometimes called showering of BG. So this ring is easy to compute, and we can proceed just as before. So use those invariants to define an equivalence relation, and thus a cobordism ring, an equivalent cobordism ring, right? But it turns out that this is not the right thing to do. Because, for instance, if we look at very simple examples, like 2 points with trivial action and 2 points exchanged by the involution, they will have the same invariance. Which means that their class in the possible equivalent cobordism ring would be the same. And I guess it's not, it's really going to be a problem since we'd like to distinguish between those varieties. I guess in general, we would like that at least the equivalent cobordism ring should contain the Burnside ring of Z modulo 2, right? And the solution is quite easy. So just replace K theory by Chow groups by K theory. So K theory has properties completely analogous to the Chow ring. So there are also Chern classes and so on. So this is an oriented cohomology theory, and we can do the same thing. And now this yields reasonable theory. So we'll be more precise in a minute and give a precise definition, but with a slight variation. So in K theory, it is more traditional to use exterior powers instead of Chern classes. So let me give the definition. So if you start with a G variety X and the partition, say alpha 1, alpha n, you can associate the invariant, say S alpha of X, defined as follows. You look at the tangent bundle, take exterior powers, possibly tensor product of those. So this is a G equivalent vector bundle, and you can think of this just as an OX module. And well, look at the corresponding coherent cohomology groups and take the Euler characteristic. So this is the alternate sum of the dimension of the coherent cohomology groups. But if you remember that there is a G action everywhere, so those cohomology groups are not just vector spaces of a K, they are in fact G representations. So what we obtain here is not just an integer, but a virtual G representation, right? And so you can use those to define an equivalence relation. And proceed just as before. So it look at the set of equivalence classes. This is a monoid. And I will denote by O of G, the associated group. Just as before, O of G is in fact a ring, and actually an L algebra. So my notation would be to X, I associate a class of X, G, in O of G. So my next purpose in this talk will be to describe the structure of O of G. But before doing this, I would like to provide a somewhat higher level point of view on what I have just explained, right? So this is just a remark. So if you have a variety X, you can consider the Chern of X and add variables, polynomial variables indexed by the integers. Let us denote this by CH bar. And there is an interesting way of turning this into an oriented cohomology theory. So the pullbacks are just inherited from pullbacks in Chern theory, but the push forwards are twisted in a universal way using those variables pi. So we'll not write precise formula, but I guess this is a well-known construction which goes back at least to Chern. Well, anyway, in characteristic 0, there is a universal oriented cohomology theory, omega, constructed by Levin and Morel, so algebraic cobordism. So we get a map like this for each X, which is compatible with push forwards and pullbacks. And the image of this map is quite easy to describe. This is the subgroup generated by fundamental classes, so by push forwards of 1 for morphisms from Y to X. Well, now, if we're in positive characteristic, there is no omega, no phi X, but still we can consider CH bar of X and also the subgroup generated by fundamental classes. So what should be the image of phi X? And essentially what we've been doing here is to use this subgroup as a substitute for cobordism. So of course, this is going to be a faithful substitute only when phi X is injective, right? And this is the case for certain X. So in particular for the point. So phi of the point is like this. This is injective. And the image, in fact, is L. So this map just sends the class of a variety X to its fundamental polynomial, which encodes, so whose coefficients are essentially the Chern numbers. So phi X is also injective, I believe, when X is cellular. So in particular, when X is a Grassmannian. And Grassmannians are approximation of the classifying space of GL. So this is somehow a justification for our definition of MR. So we essentially define the MR as omega of BGL. But now phi X is not injective when X is an approximation of BG. So those are not cellular. And I believe this accounts for the problem that appeared here. And what accounts for the solution is that if we replace CH by K theory, this turns out to be injective. This is essentially a consequence of the Haution theorem. Well, by the way, everything I just explained is valid when G is a cyclic group. But as soon as G is not cyclic, I believe that this map will not be injective. So this definition of cobordism, of equivalent cobordism, would not be reasonable. Okay, so now I can describe the structure of this ring. So the main tool is a certain map, nu, from O of G to M, so which sends the class of a variety. So recall that M is the cobordism of vector bundles. So as vector bundle, we take the normal bundle to the fixed locus. So for short, I would call this fixed data. So this will mean the normal bundle to the fixed locus of X. Right? And so in topology, it's not very hard to define this morphism. But as far as I can see, it's not so easy in algebraic geometry. I guess this is related to the fact that in algebraic geometry, in order to define cobordism, it's not sufficient to consider naive cobordism. So one has to allow certain simple types of degenerations, and that does not play so well with this map, as far as I can see. But still, it's possible to prove that this is well defined, but one has to use in an essential way, for instance, the multiplicative structure on both sides. So in fact, this is a morphism of L algebras. So the definition of this map is somewhat non-trivial, but in this talk, I will ignore this difficulty and just use this map. So in particular, projecting a vector bundle to its base, we get the map phi from O of G to L, which sends the class of X to the class of the fixed locus. Again, that's definitely a feature that we want for equivalent cobordism, but using this very elementary definition, we do not get this for free. Right? Well, another point is that I guess in application, one is really interested in the map phi. But if we try to use just this map, it's hard to do anything. And in fact, it turns out that it's a good idea to use the map nu, even if one doesn't care about the normal bundle. So it's always a good idea to carry this additional data around and maybe discard it only at the very end. So the theorem is the following. We have an exact sequence. So this is essentially computing the kernel and co-kernel of nu. So we have an exact sequence of L modules. So O of G to M. So first the kernel. So there's a map from L to the kernel, which sends the class of X to just two copies of X exchanged by the involution. So it's clear that so the action is free on such variety. There is no fixed point. So surely nu will vanish on those classes. But more interestingly, this described completely the kernel. So in other words, the equivalent cobordism class of variety X is determined by the fixed data, so the class of the fixed data in M, up to such trivial involutions. So I'm now going to describe the co-kernel of nu. So I will give a precise definition, but before doing this, I'd like to try to give some intuition. So I'm going to be maybe somewhat imprecise in the next 2 minutes, but then I will come back to this sequence. So the problem is the following. We start with a vector bundle, E over S, and we ask when is this bundle fixed data of some involution, of some G variety X. So I do not mean this literally, I mean this from the point of view of cobordism, meaning if you look at the class of E over S in M, when is it in the image of nu? This map. Well, if you allow your variety X to be non-projective, it's very easy to realize any vector bundle as the fixed locus of an involution. You just take X equals E with involution given by -1 on the fibers. So here clearly the fixed locus is the zero section, which is S, and the normal bundle is E, of course. But we were interested in projective varieties, so we may instead look at the projective completion of this. But of course, by doing this, we are going to add some fixed points at infinity. So what is the fixed data here? This is the vector bundle E plus something, namely O of 1 over P of E. So which means that E over S is going to be fixed data exactly when O of 1 over P of E is fixed data. So it may look like we are running in circles, but this is actually an improvement because this reduces to the case when E is a line bundle. And this case is actually very well understood. So let me describe this situation. So let's assume that X is a G variety whose fixed data is a line bundle. So such that the normal bundle to the fixed locus is L over S. So it is a line bundle.
Are you assuming that the group is cyclic and acts trivially on S?
So G is E modulo 2. So,
and does it act trivially on S?
Yes, yeah, it acts trivially on S. So S should be the fixed locus.
Thank you.
So I guess here, yeah, okay. So let me continue with this situation. So what does this mean? That the fixed locus is the fixed data is a line bundle. So this means that the fixed locus S inside X is a divisor, right? And this is a very special situation where the quotient is actually smooth. As far as I can see, this is more or less the only situation where this is going to occur. And if we look at the composite, this is again closed immersion, and in fact a divisor again. And moreover, in this situation, there exists a line bundle, say M over Y, such that, so first of all, M extends L, so M restricted to S is L, And second, so I said that S is a divisor in Y. So it corresponds to some line bundle Y O of S, and this line bundle is identified with M squared. So this description gives us some non-trivial necessary condition that our data L over S should satisfy. So there should exist such a variety Y and such a line bundle M over Y satisfying those conditions, right? And well, the first point is that those conditions, as we will see, are easily expressible in terms of cobordism. And the second point is that those necessary conditions are in fact sufficient, because from this data, we can recover X simply as the spec of OY plus M. So here, to make OY plus M into an OY algebra, I need a map from M squared to OY. And this is given just by thinking of M squared as an ideal of Y. Right? And the action is given just by plus on OY and minus on M. Okay, so this analysis essentially describes the image of nu. So let me reformulate this. So first we should consider the map from M to M1. So M1 is the cobordism of line bundles, which sends E to O of 1 over P of E. So this is actually well defined in terms of cobordism. And second, we should look at the map delta from M1 to itself, which sends a line bundle cell L over X to its restriction to a divisor, so where D is the zero locus of a regular section of L square. And so I guess it's not a completely honest definition. Well, for instance, because L is arbitrary, so there need not be such regular sections, right? But it's not very hard to provide a purely algebraic definition of delta using the formal group law, which I don't want to mention. So, but I guess a geometric way of thinking of this map is really what I just described. And so sequence completes using those two maps. So we first go to M1 and then model out the image of delta. So this gives a complete description of, well, the L module O of G, but in fact of OG as L algebra, because nu is a morphism of L algebras. As a corollary, for instance, we get that O of G does not depend on K, which was not completely obvious from the definition. Well, another point is that this inclusion turns out to be split. So there's a retraction which actually admits a geometrical description. And so we can write O of G as something O tilde of G. So this is the image plus, well, the image of L. Let me just write L times H. So here, H is just the class of 2 points exchanged by the involution. And so this is splitting as L modules, but it's not very hard to understand how the product behaves with respect to this decomposition. And as a result, it's equivalent to describe O tilde of G or O of G. And in the rest of this talk, I will simply consider O tilde of G, since it would be more convenient. Okay, so in principle, this gives a complete description of O of G, but it does not seem so easy to apply this to obtain concrete results. So it's useful to take a somewhat different point of view. So to look at O of G from a different angle. And well, I guess this was one of the main ideas of Boardman in topology. So for the analogous situation, that in order to understand certain multiplicative properties of O of G, it's actually a good idea to forget that this is an L algebra and just think of this as a ring. So in Boardman's case, this was an algebra over F2. In our case, this is just a ring. And so in this situation, we can construct what behave like stable generators. So the theorem is the following. We can construct G varieties xn, so indexed by non-zero integers. First of all, the dimension of xn is n. Second, the dimension of the fixed locus is integral part of n over 2. Third, we can forget about the action and just look at xn in L, in fact in L modulo 2. And those elements are polynomial generators over F2. Finally, if we look at the class in O tilde of G, so first of all, those elements are algebraically independent. And second, we can put this ring into Z, T, x1, and so on, modulo 1 relation, Tx1 minus 2. Okay, so let me comment on this theorem. First of all, it's not quite true that xn are varieties. For certain values of n, I believe it is necessary to consider virtual varieties, so possibly formal differences of varieties. So what are those xn? So as mentioned already, we can construct generators of the Lazard ring using projective spaces and min or hypersurfaces, depending on the dimension. And those xn are just the same varieties. So I guess this accounts for 1 and 3. And but there's still some freedom on the choice of the involution. And one objective is to choose the involution so as to minimize the dimension of the fixed locus. So what we have here in 2 is the minimal possible value for the dimension of the fixed locus for those given xn. And so how do we construct those involutions? So it's the most simple thing we can think of. So this really comes from representation theory. So we just say for the projective space, we just consider linear involution of the vector space and look at the induced involution of the projective space as an algebraic variety. So there is nothing mysterious here. Okay, so finally, concerning 4, I guess this inclusion is quite useful because it permits to work with elements in O tilde of G as element of a very concrete ring. And second, so those inclusions are, of course, strict. And I guess there's quite some room between those two rings. But if we invert T, those inclusions become equality. So after a certain stabilization procedure, those varieties xn behave as polynomial generators, right? So this is why I'd like to think of this theorem as a stable theorem. And as such, it's not, it's a bit difficult to use this directly to obtain for applications, right? But there is an unstable complement. So this is the following: let X be, say, an equidimensional G variety. So then there are polynomials AI such that so the class of X is the sum of AI TI. So in this ring, right? So here I'm just reformulating 4, right? But the point is that we have some control on the degree of those polynomials AI. So to talk about degree, we need to grade this polynomial ring. So first we can grade it by dimension, saying that the degree of xn is n. Then, in fact, AI has degree I plus dimension of x. I guess this just means that we want t to have degree -1, which I guess is reasonable in this ring. And more interestingly, if we grade by dimension of the fixed locus, then the degree of AI is less than the dimension of the fixed locus. And well, as we will see, just the combination of these two facts, we have immediate concrete consequences for the dimension of fixed loci of involutions. But as a remark, also, this is really an unstable result because, for instance, this gives us a bond on M. So we may arrange, I guess, M. I think the bond is maximum of 0 and 3 dimension of the fixed locus minus dimension of x. So from the previous theorem, we had absolutely no bond on M, and the unstable part is ready to say something about this M. So just by observing these relations, we can deduce quite a few concrete applications. So we'll just give a simple one, but one can consider more sophisticated things. So the situation is following: we take a G variety of dimension n, of pure dimension n, and let D, as before, be the dimension of the fixed locus. So directly from the previous theorem, we deduce the following. So take two integers, s and q, and consider the ideal of n mod 2 generated by classes of varieties of small and odd dimension. So generated by classes of y, where y has pure dimension 2i plus 1 for I in 0 and s minus 1. So if x does not lie in a certain power of this ideal, so inside n mod 2, then n is less than q plus 2 plus 1 over s. Okay, so this may look a bit complicated, so let's look at certain special cases. So first of all, consider the case when s is 2 and q is 0. Well, in particular, we get that if a Chern number of x is odd, then n is less than 5/2 of t. So this is exactly the analog of Boardman theorem. So in this sense, we can think of the theorem here as a generalization of Boardman theorem, where if we know something about which Chern number is odd, we can somewhat improve the bond. So the ratio 5/2 may be transformed into 2 plus 1 over s. And also we may have to add constant q. Right? So as an example, if we take a particular Chern number, say look at s large and still q equals 0. So you look at the Euler number, so just the degree of the top Chern class. If this is odd, then n is less than 2d. So I guess this is an analog of an even earlier result of Conner and Floyd in topology. So for an example where q is not zero, so if the class of x in the Lazard ring modulo 2 is indecomposable, so in any graded ring, we have the notion of indecomposable elements, then n is less than 2d plus 1. Okay, so those are a few special cases. And I guess those types of results are probably the most desirable because we make an assumption on x, which does not depend on the g action. So it's just about the geometry of x, right? And the conclusion is a restriction for any g action. But if we are willing to make assumption on the fixed locus, we may have somewhat more precise statements. So those statements are somehow of a different type. And as far as I can see, they were not really considered in topology. So let me, the analog of the first one would be that if a Chern number of the fixed locus is not divisible by a certain power of 2 q plus 1, then n is less than q plus 5 half of d. There's also a version of the second statement. So if chi xg is not divisible, then again we have to add q. So maybe one can understand the origin of the difference between those two types of statements by drawing a simple diagram. So we look at O of G, and there is a map to L where you just forget the action, right? But if you remember, our main theorem was about O tilde of G. So this is a quotient of O of G. And so in this quotient, we have to kill one element, namely H. So H was 2 points exchanged by the involution. And of course, this goes to 2. So which means that if we want to complete this diagram, we have to go to L mod 2. I guess this accounts for those types of results where we have to look at the parity of Chern numbers. But now we can go to L using the map that I called phi, which sends x to the fixed locus. And now, of course, h is sent to 0, so we can really get a map like this. And this explains why we have integral results here. Okay, so I'd like to conclude with a few statements in a somewhat different direction. So what happens when the dimension of the fixed locus is very low? So the extreme case is when d is 0, which means that fixed points are isolated. Then, well, it's quite easy to see that there is essentially one element. This is x1. So, well, lambda is an integer. So this has to be a multiple of a power of x1. And so x1 is just p1 with the involution fixing 2 points. So we can even count fixed points. So the number of fixed points, well, so over k bar. is precisely lambda times 2 to the n. But more interestingly, this type of description generalizes to somewhat higher dimension of the fixed locus, but still low compared with M. So when the dimension of the fixed locus does not exceed 1/3 of the dimension of the ambient variety, so when n is greater than 3D, then the class of x in O tilde is actually a polynomial in the xi, in x1 and so on. And moreover, this polynomial is divisible by a certain power of x1. X1 n minus 3d. So which means that, so recall that we had this inclusion here. This means that in a certain range of dimension for the fixed locus, this is actually an equality. So meaning that in this range, well, really everything comes from representation theory, from very simple type of actions. Right? But I guess as soon as we go out of this range, there are some more mysterious involutions. So to conclude, let me make maybe 2 remarks. So this is still about this case when n is greater than 3D. So first of all, in this situation, well, essentially involutions extend to GM actions. So again, not literally, but from the point of view of cobordism. So this means that there are GM varieties. So a GM variety Y, possibly formal difference of variety, such that X has the same class as Y in the Lazard ring modulo 2, and the fixed loci are the same also. So xg is equal to ygm, which is equal to yg in L. And second, so maybe somewhat something that might seem surprising initially. So the class of the fixed locus in the Lazard ring modulo 2 is determined by the class of X. So this is definitely something that seems very wrong if we do not assume that D is small, but this turns out to be the case in this range. Okay, so I guess I will stop here.
Thank you very much. Thank you. Is there any question? Any question? Any question?
Do you have similar results for other cyclic groups, larger cyclic groups?
Yeah, some weaker results. So I believe that the case of Z modulo 2 is really exceptional. And so it's not just that proofs are simpler or there are fewer cases to consider and so on, but it's also the case that certain statements are really specific to Z modulo 2. But, well, some statements also generalize to other primes. So perhaps my guess is that the sequence here, there should be a version for Z modulo P, at least. So I don't know how to, even how to state it or how to prove it, but I guess that Tom Dick has result in this direction in topology, so we expect that the same should hold in algebraic geometry. But of course, this analysis here was extremely dependent on the fact that we had Z modulo 2. So this definitely doesn't work for other groups. So these stable generators, I don't know. I would be surprised that something such a simple description exists, but I have no precise idea. Well, those types of results, again, are very specific to the modulo 2. But by contrast, this one, I believe this generalizes to any cyclic P group. And moreover, it should generalize to any abelian P groups, provided that we modify somewhat the statement. So there are definitely things valid for other P groups, but it's actually quite interesting to try to understand what is specific to the modulo 2 and what is more general.
Some more questions? More questions?
So can you comment a little bit about why exactly is it hard to realize geometrically, like directly the morphism, basically taking the fixed locus? Sorry, you mentioned earlier.
So you
Like
mean the morphism nu?
I think so.
So this one?
Yeah, that one. Yeah, so what exactly goes wrong? So it has something to do with the double point relations then?
Well, actually, my proof doesn't use at all the double points relation because this works in any characteristic, well, different from two. So,
sorry, but my question is, or was that, I mean, you mentioned that it's hard or you cannot do this directly, construct such a map. Like,
yeah, I cannot do this directly. I guess if we try just to so of course it's I choose a different definition of O of G. So probably that was not so. Well, I was just saying that in the end this should be related with the difficulty with the appearance of these double point relations, but well, the proof doesn't go in this way, so I'm not sure whether this was such a helpful comment, but
okay.
More questions? More questions? If not, then let's thank the speaker for a wonderful talk. Thank you very much. And we will resume in 1 month, right? Well, a bit less than 1 month, on May the 5th.